Hello aspirants, welcome back to the another session of basic electrical engineering. So in previous session we have discussed laws of resistances, okay, then Ohm's law. So with that we have studied cells and batteries, what are the different types of cells like primary cell, secondary cell, what are all the advantages, okay, and what is battery efficiency, whatever efficiency, all the things we have discussed. So today we are going to discuss about magnetic circuits, electromagnetic induction, AC fundamentals and AC circuits, single phase, polyphase. Okay, so without any further delay we will start now. So magnetic effect of electric current, magnetic effect and magnetic effect of electric current. Okay, what is this magnetic effect of electric current? We'll see. So whenever a current flowing through a metal, okay, so we have one metal, so current is passing through it, then a magnetic field will be produced around this metal. Okay, whenever a metal is there and current is passing through it, there will be a magnetic field around it, okay, which is called as magnetic field of electric current. Magnetic field of electric current. Okay, so to know how the magnetic field and direction of current is followed, then we have two rules. Okay, what are the two rules to find the direction of electric lines of forces? That is what magnetic field, direction of lines of force or magnetic field lines. Okay, so one is right hand rule or thumb rule. This is not right hand rule of Faraday, okay, Maxwell. So what this right hand rule says, okay, whenever a current carrying conductor is gripped in such a way that this thumb will indicate direction of current, okay, then other fingers have of the hand, what they will do? Direction of magnetic field lines. Okay, thumb will indicate the direction of current. Okay, whenever the current carrying conductor is gripped such a way that the thumb indicates what? The direction of current, where these fingers will indicate the magnetic field around the conductor. Okay, so this is how the magnetic field lines are surrounding the current carrying conductor. Okay, then we have corkscrew rule. Corkscrew rule. Suppose if you take a screw, okay, so you will be having a screw, correct? So the direction where the screw is pointing is called as current direction. Okay, when you rotate this in clockwise, okay, that will gives you magnetic field lines direction. Okay, understood? Whenever the screw is pointing, this tip is saying you the current direction. Whenever you rotate this screw, what it will do? It will gives the magnetic field line direction. Okay, so if we talk about the polarity of solenoid, what is this polarity of solenoid? See, you will be having a solenoid. Okay, in order to know the direction of what, so the polarity of a magnetic field produced by a solenoid can be determined by the following rules. What are the two rules? One is helix rule, okay, and end rule. So what this helix rule will say? So according to this rule, solenoid is gripped in a right hand, okay, the same way. Okay, here thumb will say, okay, fingers pointing the direction of current. Okay, the fingers will be pointing now here, so fingers pointing will show current direction, whereas thumb says direction of north pole. Okay, this is what helix rule, first rule, helix rule. What it says, whenever a solenoid is gripped in a right hand such that the thumb indicates the north pole direction, whereas other 4 fingers will indicate the direction of current. So now we talk about the end rule. So end rule says that if you find one pole, okay, if you find one pole, solenoid current direction is in clockwise direction, okay, clockwise direction, then that pole is south. If the current direction in anti-clockwise, if the current is clockwise, then it is called south. Anti-clockwise, current is north pole. So direction is pole is in north pole, not current. Okay, so current direction in clockwise, anti-clock, in clock direction south pole, current direction in anti-clock will gives you north pole. This is end rule. Okay, so we'll discuss some important magnetic terminologies. Okay, so first we'll see magnetic field. Okay, what is magnetic field? We have magnet. Okay, say this is north and south. Okay, so here what is magnetic field? The free space around this magnetic field, or the free space around the magnet which are influenced by the magnet, can be defined as magnetic field. The space around a magnet in which the influence of magnet can be detected is called magnetic field. So now we have magnetic flux. Okay, so what is this magnetic flux? So magnetic flux is nothing but a group of magnetic lines. Okay, now we have group of magnetic lines. Okay, these are group of magnetic lines. So what it says, a group of magnetic lines of forces is called magnetic flux. Remember this, and it is denoted as phi, and its unit is Webers. Okay, so if we talk about magnetic flux density, what is this magnetic flux density? So it is denoted as B. Magnetic flux density is defined as the magnetic flux per unit area. Suppose we have one area here, say this is area. So here how many flux lines are lying or passing? That is called as magnetic flux density. Okay, magnetic flux density is defined as magnetic flux per unit area is nothing but magnetic flux density. So we have a mathematical equation B equals to phi by A, where B is magnetic flux density, phi is flux, A is area, magnetic flux density. So area in meter square, remember that. Flux or magnetic flux in Webers. See, many questions will be asked based on this formula only. Please remember this formula. Okay, so now if we talk about magnetic induction, what is this magnetic induction? Anybody knows magnetic induction? So magnetic induction is nothing but whenever a magnet bar So we have magnet bar is placed near an iron. Okay, this is magnet iron. Whenever magnetic bar is placed near the iron, then iron piece is magnetized in opposite polarity. This process of magnetization is called as magnetic induction. So what happens? Magnetic what happens? Once again I will tell you. Whenever a magnetic bar is placed near to iron piece or iron bar, so then the iron piece is magnetized. This will get magnetized in opposite polarity. Okay, this process of magnetization is called as magnetic induction. So now we have magnetic circuit. What is this magnetic circuit? We will see now. So magnetic circuit means the closed circuit formed by magnetic lines of force is called magnetic circuit. Okay, so now we have MMF, that is magneto motive force. So in electrical circuit we have EMF, electromagnetic force, whereas in magnetic circuits we have magneto-motive force. So like EMF, as I said, in magnetic circuits MMF provides what it will provide? Magnetic flux to the magnetic circuit. Remember this. So mathematically MMF is equals to number of turns into current, that is MMF is equals to Ni. What is the unit? Ampere turns. So next we have reluctance. Where we have resistance in electrical circuit, we have reluctance in magnetic circuits. Same as resistance in electrical circuit. Remember this. Okay. So in magnetic circuit there is something analogous to electrical resistance, correct, and it is called as reluctance. In a magnetic circuit there is something analogous to the electrical resistance. It is called as reluctance. How reluctance is defined or represented? L divided by mu naught mu r A. Okay. So reluctance, so let me, reluctance means Rm, reluctance of magnetic circuit. This is reluctance in ampere turns per Weber. Okay. So now next we have what we have? L, length of magnetic coil. Mu naught and mu r are the permeability of free space and permeability of medium. Permeability of free space. Mu r is nothing but permeability of medium. So mu r equals to 1 when for free space. Okay. So next we have magnetic flux. Magnetic flux. What is this magnetic flux? Magnetic flux through any surface is the surface integral of the normal component of the magnetic field B passing through that surface. Okay. Magnetic flux through any surface is the surface integral of the normal component of the magnetic field. B passing through the circuit or through that surface. Magnetic flux is nothing but current in electrical circuit. Okay. So for that, phi is equals to integral of surface integral B dot ds, that is Ni by Rm. See, this Ni is nothing but what? Magnetomotive force. R is nothing but resistance. So here when we compare with electrical circuits, V by R, I is equals to V by R, whereas magnetic flux phi is equals to Ni by Rm. Okay, or phi is equals to Ni A mu naught mu R by L. So we have extended this Rm further. So we got this equation. So we have one other important term, that is permeability. Okay, what is that? Permeability. What this permeability says? It is the ratio of magnetic flux produced by a given magnetic force of the material or medium to the magnetic flux which would be produced by the same magnetic force in a perfect vacuum. So it is denoted as B divided by H. Remember this much. Okay, you remember this formula, and there is no unit for permeability. You just remember this formula. Okay, so then we have residual magnetism. Okay, you might be studying in machines this. What is this residual magnetism? It is the magnetism which remains in the material, when the effective force has been reduced to 0. What is residual magnetism? Which remains in the material when the effective force has been reduced to 0. Even though when you reduce voltage to 0, there will be some residual magnetism. Okay, stored. So next we have magnetic saturation. What is this magnetic saturation? The limit beyond which the strength of magnetic cannot be increased. The limit beyond which the strength of a magnetic cannot be increased is nothing but magnetic saturation. So we have susceptibility. What is this susceptibility? It is defined as the ratio of intensity of magnetization, ratio of intensity of magnetization to the field intensity. So these terms will be coming in examination. They won't be asking you any formula, they might be asking you definition, what is susceptibility. They might be given this answer as one of the option. Okay. So next we have hysteresis. This hysteresis will come along with every subject. Okay. Everywhere, measurements, machines, wherever you go. What is this hysteresis? It is defined as the magnetization of flux density. Magnetization of flux density that is B behind the magnetization force H. So you might be seeing that BH curve, right? So it will be like this. Okay, somewhat like this. This is what BH curve. So if we talk about the classification of materials, magnetic material, so on the basis of permeability, magnetic materials classified based upon their permeability. So we have three. One is ferromagnetic material, another one is paramagnetic material, we have diamagnetic material. Okay, what are the difference between ferromagnetic material, paramagnetic material and diamagnetic material? See, if we talk about the ferromagnetic material, these are the materials which gets magnetized in the same direction of the field and remains magnetized even after the removal of field. Example, iron, nickel, then we have cobalt and their alloys. What are the ferromagnetic materials? The ferromagnetic materials are where they get magnetized in the same direction of the field and remains magnetized even though after removal of field. Such materials are called as ferromagnetic material. Then we have paramagnetic materials. The materials when placed in a magnetic field acquire weak magnetization. Okay, in the same direction of field is called as paramagnetic material. Example, we have copper, aluminum, platinum, etc. So next we have diamagnetic material. The material which is placed magnetic field does not acquire any magnetization. So example, bismuth, antimony, water, etc. So the value of permeability is slightly less than 1. Okay, permeability value less than 1 for diamagnetic material. So if we talk about next, electromagnet. What is this electromagnet? If a soft iron bar is placed in a magnetic field or inside solenoid or coil, and DC current is passed through it, then the electric field produced is strong, and this forms electromagnet. So we have solenoid. When you place conductor, or conductor is covered by this solenoid, forms a magnetic electromagnet. Okay. So what is electromagnetic induction? Electromagnetic induction is the phenomena of a production of electric current or EMF in a coil when the flux linked with the coils changed. Okay. So we will study about that with Faraday's law of electromagnetic induction. What it says? So with reference to Faraday's law of electromagnetic induction, Michael Faraday has given two laws. Okay. First law, what it says? Whenever the value of magnetic flux passing through any conductor changes, the value of flux changes while passing through conductor, and then an EMF is generated in the conductor, and this EMF is generated, and the generated EMF retained until the value of flux is variable. Flux is variable. Okay. Of is nothing but Faraday's law of electromagnetic induction. So whenever the value of flux changes while passing through the conductor, or let us say whenever the value of magnetic flux passing through the conductor changes, then the EMF is generated in the conductor, and this EMF is retained until the value of flux is variable. The second law says, the induced EMF E in any closed circuit is equal to the rate of change of magnetic flux linking by the circuit. So mathematically E is proportional to phi 2 minus phi 1 with respect to time. Okay, that is E is minus n d phi by dt. Here E is nothing but EMF in volts, n is nothing but number of turns, then we have d phi, rate of change of flux, then we have dt, time in second. Okay, so as we know that E is equals to minus n d phi by dt is the induced EMF, where here negative sign indicates the induced voltage acts opposite to the direction of flux. That is Lenz's law. Okay, so induced EMF we study now. How the induced EMF? So now we will study about the induced EMF. What is this induced EMF? Induced EMF nothing but the EMF produced in a conductor with the help of electromagnetic induction. EMF produced in a conductor with the help of what? Electromagnetic induction is called EMF. So we have two types of induced EMF, two types of induced EMF. One is dynamically induced EMF, another one we have statically induced EMF. So dynamically induced EMF equals to BLV sin theta. So here B is what? Magnetic flux density, correct? L is nothing but length of conductor. Then we have V. V is nothing but speed of conductor in meter per second. Okay. So we have statical induced EMF. So here dynamical induced EMF is nothing but whenever a conductor is moved in a magnetic field in such a way that it cuts the magnetic field lines or forces, and an EMF is induced in the conductor, is nothing but dynamically induced EMF. Statical induced EMF means whenever a conductor is placed in a alternating magnetic field, then magnetic flux cut itself and an EMF is induced. This induced EMF is called statical induced EMF. Mathematically E is equals to minus n d phi by dt. Okay. So this is what? Statically induced EMF.